All right, so 4.3, I think the video and the audio is going to be off on this video now because it like skipped a number. Usually that means it's off, but it's fine. So 4.3, derivatives of inverse trig functions. Push it up a little too far. Somebody put all my markers in here upside down so I can't see what they are. Alright, so we'll start out with the theorem. Alright, so derivatives of inverse functions. So this is just going to be inverse in general, so basically overarching all of them. If f is differentiable at every point of an interval I and df dx is never 0 on I, then f has an inverse and f to the negative 1 or f inverse is differentiable at every point on the interval f of I. So I is basically just the interval that you're looking at. A lot of times, like in college, when we were talking about an interval, we would just say from A to B. So we would say I is equal to A to B, basically. So you can just think of that as whatever the values are that are in your interval domain, whatever it is you're talking about at the time. That's how you can kind of think about the I there. Alright, so obviously, this being trig functions, we're going to start with some of those. So they're kind of interesting in the sense of what they end up looking like and stuff like that. So it'll probably take us a couple of days to get through this stuff too, just to really understand it. But the derivative of arc sine or sine to the negative 1, depending on how you prefer to write it. So I'm going to switch to a smaller marker so I can get all this here. Alright, so x is equal to, we're kind of going to derive it here. So x is equal to the sine of y is differentiable in the open interval negative pi over 2 less than y less than pi over 2. And its derivative cosine is positive there. So that's already stuff that we know. So then by theorem 1, y is equal to the arc sine of x is differentiable through -1 less than x less than 1. Okay, because remember, sine goes from -1 to 1. Okay, but the reason we don't include -1 and 1, so basically it can't be differentiable. I'm going to just write DIFF for differentiable because it just takes too long to write it. At x is equal to -1 or x is equal to 1, because tangents of the graph are vertical at that point. So then actually getting into now the derivative of it here. The derivative of y is equal to the arc sine of x. We can say the sine of y is equal to x, okay, because of the inverse relationship. Okay, if we differentiate here, if I take the derivative of this side, what do I get? Yep, cosine y prime. And then on the other side, 1. Okay, differentiate / implicit. Okay, which you recognize, so that was good. So then we want to get y prime by itself, so that gives us y prime is equal to 1 over the cosine of y. Alright, so this is where it gets a little interesting here. And obviously you're not going to have to derive it on the test. This is just so you can see where the first one comes from, because I can pretty well tell you you're not going to want to derive them because they're not fun to derive. So then from here, we know that the cosine of y is not equal to 0 for minus pi over 2 less than y less than pi over 2. Okay, because basically the pi over 2's aren't included, meaning it's not going to be 0. And so actually, the cosine of y is positive. I feel like this got really, really out of focus, so give me a second to... I don't really think it started out super in focus, but a little better maybe. So then we're going to replace the cosine of y with the square root of 1 minus the sine of y, and that's squared the sine of y. Okay, and then from up here we know that the sine of y is x, so this is the square root of 1 minus x squared now. So essentially, in short, we can say that the derivative of the arc sine of x is equal to 1 over the square root of 1 minus x squared. And then we're going to make a little note here for what happens if it's not just an x there when we're taking if I say not an x here, if it were like the arc sine of x squared plus 2, like what you would have to do with that. So we'll generalize it here a little bit. So I'm blanking on the name of it. sine squared plus cosine squared is equal to 1. Basically, you can just get that. So basically 1 minus the sine squared, and then take the square root of it. That's where they get that from. So yeah. It's one of the Pythagorean identity. There we go. And I actually write that in just in case. Just in case I ever need to use these videos in the future. And somebody be like, what is she talking about? Something in my eye. Okay. So then generalized, basically, if u is a differentiable function, okay, meaning that's what's going to go here for x. So, like if we add the x squared minus 5, that's a differentiable function. So, if it's a differentiable function of x with the absolute value of u being less than 1, we apply the chain rule. Which basically just means then that if I have d dx of the arc sine of u, we get 1 over the square root of 1 minus u squared times du dx, okay, which is the derivative of that the u equation for the absolute value of u being less than 1. And that's the official end of that kind of proof there that we did to get that one. Can't remember. We'll kind of derive the tangent one and then arc secant. Okay, yeah. So we'll do sine, tangent, and secant, and then cosine, cotangent, and cosecant come from those. Basically, all of these ones are going to be positive, so notice like the sine one is positive. The cosine one is going to be identical, but it's going to be negative. So if you memorize the 3, all you have to know is whatever one it matches up with is negative. And I will say these are really hard to remember, so. Alright, so let's look at the derivative of arctangent then. And we'll get into examples of these tomorrow. I'm not going to do examples today. We're just going to get through the notes of it. Alright, so then the derivative of arctangent. These ones will go a little faster because we're not going to be writing all that extra little stuff about showing that it's differentiable and all that. We'll briefly talk about it, but then we'll just go through and get the whatever I'm trying to say. Words not happening. Get the result, I guess. So y is equal to the arctangent of x is defined for all real numbers and is differentiable at all real numbers. So then we start out with the same kind of deal. Y is equal to the arctangent of x. So then we can say then that the tangent of y is equal to x for the inverse function relationship or the inverse relationship like we did with the previous one. So then we can take the derivative of both sides. So what would my derivative over here be? Yep, secant squared y prime is equal to 1. So this is differentiate / implicit. So then I want to get y prime by itself, so that's going to give me 1 over the secant squared of y. Now, do you happen to remember what the Pythagorean identity is for secant squared, or the one that deals with secant squared? if you start with close. How would I get from here to get a secant? What would I have to divide by to get a secant? Or which of these, yeah, which of these would I divide? Which of these two would I divide this by to get a secant? Yeah. Yep. If I can write. So then basically we can rewrite this bottom part as 1 plus the tangent squared of y. Or the tangent of y squared, either way. It's a little bit easier to see if you write the squared outside to actually get it, but it doesn't really matter because eventually, like I said, you're not going to actually have to do these. So then basically we know that from up here, the tangent of y is equal to x, so I can replace that with x squared. So 1 over 1 plus x squared. And then this is defined for all real numbers. I'm just going to do the fancy R to show that that's what that means. So again then, same thing with u. Basically, I'm just going to write the u version out. Just know that it means all the same stuff as it did in the previous one. Basically, d dx of the arctangent of u is 1 over 1 plus u squared times du dx. So just taking the derivative of u. So this is for the chain rule of that particular one. All right. So then we have one more. Probably going to go to a new page because this one takes a little bit more space here. If you don't have a decent amount of space left, you might want to go to a new page if you want the whole thing on one page. So the derivative of arc secant. So something that we just kind of need to remember here, or whatever, is that y is equal to the arc secant of x for the absolute value of x being greater than 1. So then secant of y is equal to x for the inverse relationship. If I want to take the derivative of both sides, what do I get for this one? So since this is all one derivative, we just have to write the y prime once. Yeah. If we were taking the second derivative, obviously, then you have a product rule, and then you would have all that stuff added in. But so then getting that by itself, y prime is equal to 1 over the secant of y, tangent of y. Okay, so this one's where it gets a little weird, and this part, just trust the process. since the absolute value of x is greater than 1, y lies in 0 to pi over 2 union pi over 2 to pi. And secant of y, tangent of y is not equal to 0. So this is where it gets a little interesting now, because we now have two things on the bottom. So previously, we've had like 1 plus something or whatever it was, and 1 minus something. And so we've just replaced whatever we had with the initial stuff that we knew here. Well, I know secant of y is x, so that's taken care of. So that's taken care of, but then we have the tangent of y, which we need to figure out how to rewrite it. So, hold on a second. I need to make sure this is written correctly before I end up with signs wrong. Okay. Yeah, we're good. All right, so tangent of y, we kind of said earlier, obviously, is the, 1 plus tangent squared is equal to secant squared. So now we need to get tangent by itself, basically. So this is going to be plus or minus the square root of secant squared of y minus 1. So basically, this is going to give us then, because secant is x, we're going to say this is plus or minus the square root of x minus 1. So then rewriting everything, we would see that dy dx k or y prime is 1 over x times the square root of x squared minus 1. But we have this plus or minus here when we're multiplying, so we're going to throw that out front. So now basically, in order to kind of take care of that, this plus or minus, to not have to deal with it, we are going to say that the arc secant of the derivative of this is equal to 1 over the absolute value of x times the square root of x squared minus 1. So basically, by putting that x in the absolute value bars, that takes care of the plus and minus option. And then, obviously, dealing with the chain rule. If we have the derivative of the secant, arc secant of u, we have 1 over the absolute value of u times the square root of u squared minus 1 times du dx, given that the absolute value of u is greater than 1. So you'll kind of be able to think of this type as, well, a chain rule, obviously, because most of the time it's not just going to say, tell me what the derivative of arc cosine is. Like, they're not typically just going to say that. They're going to give you something in there for x. So basically, you can kind of think of it like when you're just solving a function. You're taking whatever you had in that x value and just sticking it in the equation and then solving for it. Okay, so I told you that the other ones, basically, they just come straight from it. You just do, like, the negative of whatever you have to start with, which is true. So I'm going to kind of show you where they come from a little bit. briefly here, and then I'll give you a full write-up of what all 6 inverse trig functions are in the same place that we have them all together. Should have written inverse there. Now that really doesn't look like inverse. All right, so these are going to be cofunction identities, okay, and then I'm going to also show you on your calculator what the conversion looks like as well here in writing. So the inverse function, inverse cofunction, identities, so the arc cosine is pi over 2 minus the arc sine of x. The arc cotangent of x is pi over 2 minus the arc tangent of x. And then the last one of those is cosecant. Arc cosecant is pi over 2 minus the arc secant of x. So that's how you get them if you don't know them off the top of your head, but that's kind of a pain to actually figure out when you're doing it. It'll be easier just to plug them into the little formulas. So then we also have calculator conversion identities, so just so you can see how they convert on your calculator. So basically, arc secant of x is the arc cosine of 1 over x, which that kind of just makes sense anyways, because secant is 1 over cosine, so it kind of makes sense. It just changes what's inside. Cotangent, or the arc cotangent, is pi over 2, hold on. I think I wrote. Nope, that's right. Okay. So this one doesn't really change. You still do pi over 2 minus the arc tangent of x. So that one's basically the same as it was up there. But then cosecant, arc cosecant of x is the arc sine of 1 over x. So that's where those come from. And then we'll write out the all six here on one page. Need more paper. Really banking on having enough. All right, so all 6 inverse trig derivatives. All right, and I'm going to write them side by side so you can see what they go with easily. So we have the derivative of arc sine of x is 1 over the square root of 1 minus x squared. And then its pair is the derivative of the arc cosine of x, which is 1 over the square root of 1 minus x squared, but this one is negative. The derivative of the arc tangent of x is 1 over 1 plus x squared. And then its pair would be the arc cotangent, of x, which is negative 1 over 1 plus x squared. And then the last ones here, we have the derivative of the arc secant of x, which is 1 over x times the square root of x squared plus 1, or oops, this is supposed to be a minus 1. There we go. And then its pair is the derivative of the cosecant, or arc cosecant of x, is negative 1 over x times the square root of x squared minus 1. So we take the absolute value off because one of them is going to be positive and one of them is going to be negative. What we did earlier just gave us both of them at the same time, basically. And I'm not actually sure if all 6 of these are listed in your book in one place. So that's the other reason for writing them down, because I don't think that at any point in this section they actually list out all 6 for you, which is really annoying. Because that's why last year I was doing them and I was like, what in the world? Like, it'll just tell you, well, the other one's the negative of it. And I'm like, but it still really should write them out because you do really need them. So anyways, but we'll call it for today, and Monday we'll look at some examples.